Hey folks, this is Todd Coburn with Cal Poly Pomona with lecture 12 of Arrow 4080. Today we're going to look at, once again, hand analysis, finite element analysis, and we're going to look at dealing with beams when we have a nodal hinge, where there's no moment carrying through. Okay, let's see how it works. If we take a quick look back and recall what we found for beams, we were reminded of beam sign convention and then the coordinate system that we're going to use when we're analyzing beams using finite elements. Okay, that's shown on the left. We know what the local stiffness matrix is for that beam element, and we know how to account for shear stiffness and shear flexibility. All right, so with that said, we're ready to start looking at, so what happens when we have a nodal hinge? So suppose we have a hinge in the middle of a beam, which means a point where there's like the two pieces are pinned together so there's no moment transferred through. So the beam can still deflect there and it can have rotation there, but there's no moment carrying capability through that part of the beam. For example, this beam here, 3 nodes at node 2, if we have a nodal hinge, how do we analyze that? Okay, so we can look back at our coordinate system, right? When we do this, we say, okay, for this particular beam, we have 3 nodes and 2 elements, okay? And we can actually idealize or model that hinge either at the right end or the second node of beam 1 or at the first node of beam 2. But we can't do it at both, okay? Either the first node of the second element or the second node of the first element. Okay. Now, Logan shows how he shows the derivation of that. It's a rather lengthy derivation of how we remove that. Actually, it's not that lengthy. Basically, what we're doing is we're saying we're purging out the moment. We're not allowing that moment to be carried through. So we're purging that out of our system of equations. Now, when we do that, it just adds a little bit of a trick to getting all the results that we need. So we can understand it by just simply realizing that we're going to tweak the stiffness matrix of that particular element according to where we're eliminating the moment carrying capability. So let's say we already know what the local stiffness matrix is for a beam element. And if we decide to model the hinge at the second node of the beam element, then we will modify our stiffness matrix by removing the rotation out of the system equation. Normally, it's that rotation that gives it the moment at the second node. By eliminating the rotation out of that stiffness matrix, we're not going to couple the moment and rotation at all. That allows us to calculate the rotation from other parts of the system of equations and then back solve for the rotation at the node we need. So what we're going to do is we're going to take our basic stiffness matrix, and if we're modeling the hinge at the second node, we will just eliminate the row and column corresponding with the FEA, or the rotation of that element. If instead we decide to model it at the first node of the other element, then we will eliminate the column associated and the row associated with rotation there. That decouples the system so we can go and calculate the rotation in another manner. Okay, so for our purposes, all we do, calculate our local stiffness matrices in the normal way. If we decide we're going to have a nodal hinge, what we do is eliminate the last row and column if we are modeling it at the second node, and if we are modeling it at the first node of the element, then we'll eliminate the second row and column of the local stiffness matrix. That gives us a 3 by 3, but an easier way to do that, instead of using that 3 by 3, is just to make all those zeros in our local stiffness matrix. So the size of our stiffness matrix remains unchanged, and we just zero out those rows and columns. Okay? With that said, we then can, this is explaining what we just did, and now we have to take care. So we impose the nodal hinge by first selecting the element and the node on that element that we're going to impose the hinge on, changing the local stiffness matrix for that element. And then we're going to find the global displacements will be the value on the other end of the adjoining element. So if we decide to model the hinge at the second node of element 1, we will actually get the displacement and rotation from the other element at the first node of the other element. Okay? We'll see how that plays out in a moment. And then what we'll do is go back to the normal stiffness matrix, the unmodified stiffness matrix of the element, in order to calculate what the rotation is on the other part. So let's say we have a stiffness of two beam elements like this, and let's say this is element 1, this is our hinge, this is element 2. If we model the hinge on the second node of element 1, then we're going to purge that degree of freedom by modifying the stiffness matrix for element 1. We then are going to solve our system in the normal way, and when we're done, we're going to get a displacement and a rotation, and those are actually coming from the other node, from the node on the other element. Then to get the actual rotation, we already know the moment on this one is 0. To get the rotation on this node in the first element, because you'll see the 2 rotation, it does have a rotation and it's different than this one. It may be the opposite of that if you have a symmetric system. It may be something different if it's not symmetric. But basically what we'll do then is we'll go back to the original stiffness matrix, we'll plug in the displacements of this element, and we'll back solve for the, or put in the forces for this element, and then we'll back solve for the rotation at that element. Okay? We'll see that on the next slide again. So here's our little method, our little modified method. We're going to model our system in the same way we always do. Okay? We're going to choose which of our 2 beams, right? If we have a hinge, it's going to be between 2 beam elements or 2 types of element. Right now we're just looking at 2 beam elements. Either it'll be on the second node of element 1 or the first node of element 2. We'll choose which one we're going to do. Once we choose the element, that will tell which node, whether it's the first or the second node, where the hinge is. Okay? We're going to determine our stiffness matrix, our local stiffness matrix for each beam element. This means we've got a local stiffness matrix for all of them, and for the one where we have the hinge modeled, we have a little bit of a modified one with that column and row zeroed out. We're going to use our stiffness, each of those local stiffness matrices then, and we're going to construct our global stiffness matrix. Actually, first we will transform into global coordinates. We're not doing that yet. We'll do that later. Right now we're just assuming everything's going to be aligned along the global axis. We assemble our global stiffness matrix in the normal manner, and we imply our boundary conditions in the normal manner. Okay? We're going to solve our system, and that's going to give us the displacements. The displacement will be for the node where the hinge is. The transverse displacement will be correct for both nodes. Or actually, it's one node, 2 elements, right? The rotation will actually be the rotation of the element where the hinge wasn't modeled. So if we model the hinge on the second node of element 1, then the rotation that we get out of our system of equations will actually be the rotation of the other element at that node. We'll have to do another little step to calculate the rotation on that element where we modeled it. If we instead had modeled our hinge, our pin, on the second element, then the rotation that we get out of solving the system equations will actually apply to the other element that we didn't model the hinge on. And then to get the rotation on this element where the hinge wasn't, we will then use the forces and moments with the original stiffness matrix before it was tweaked for removing the hinge in order to calculate that. We'll see how that works as we go. So once again, we're using that reduced system to calculate our displacements. Once we have our displacements, we're going to use those displacements to determine the global forces. Once again, that will give us the external forces on the system. Okay? Now we can go and move forward in what we're doing. So this is just a note. We don't actually need this note here, but what we're saying is, once again, if we have a hinge on any bar elements, whenever that happens, remember the rotation that we're going to get for the element. If we model the hinge on this element, the rotation that we're going to get out of our system equations is actually the one corresponding with this. You'll see this would be a positive rotation, right, that moved up like this. On this one, the one we model the hinge, is actually going to be a negative. We're going to have to do something else to calculate the rotation on this element. We're only getting the rotation of the other element. If instead we had modeled the hinge on the first node of the second element, then when we solve our system equations, the phi that we get, the rotation, is actually the rotation of the one we didn't model the hinge on, and we'll have to do another step to get the rotation on this hinge. That's what this node is talking about, okay? All right, now that we have the displacements, we can use the global displacements on each node as normal with the global stiffness matrix of each element to calculate the forces in each element, okay? So we know what all those are for everything in our model except for the displacement in the bar where we didn't model the hinge. The one that we didn't model the hinge in, right? If we model the hinge on the first bar, second node, then the rotation is the rotation from the other, is the rotation associated with that node on the other element, okay? So is the rotation from the other element. The one that we get is the rotation on the bar. And then what we're going to do is plug in our forces and moments on the other bar, and with our local stiffness, make sure we can back solve that, which means solve the inverse of the system, because we've got one unknown, and that's the phi of that non-hinged bar. That's where we'll get it by back solving that, okay? So basically, that's what this says. It says once we do this with all the ones that we have, we then will go and take, this is the stiffness matrix of the element that's adjacent to the hinge, but the one where we didn't model the hinge. You'll plug in the forces for that and solve for these displacements. You will have all the displacements except for the one rotation that we didn't have before. Okay? All right, here's some examples. So let's say we have a bar like this with a hinge there. So let's say that we first decide to model it, the hinge, on element 1's node 2. That's the second node. Okay? These are we got 3 nodes, we have 2 elements. All right? So now we're going to go and calculate our stiffness matrices. This is our general stiffness matrix, and because for all elements we've got this first stiffness matrix, but for the one where we have the hinge at node 2, we have this other stiffness matrix, okay? We now can go and you can see for element 1, so you're going to see actually 2 stiffness matrices here for each element. This is just my own nomenclature. Actually, it's the second one is the actual stiffness matrix. This first one, KELP, is the local stiffness matrix without the 3EI over L cubed. This just makes it easy for me to check to see that matrix makes sense. We can see that's just 1 in the first spot, the length in the next spot, the length squared in the next spot, and so on. So this is just a way you can just look. The second one shown for each is the global stiffness matrix of each element. The first one shown is a partial stiffness matrix without all the terms multiplied out, okay? We then are going to use that and construct our global stiffness matrix of the entire system. Once we've done that, we can apply our boundary conditions. We see that we are fixed at this end and at that end, right? And now we can go and solve our system in the regular way. Since we've already accounted for that hinge in our local stiffness matrices, we can just solve like normal for the next couple steps. So we solve for our displacements. So we're going to get the displacement at node 2, and we're going to get the rotation of node 2 in the other element. Since we modeled the hinge on the first element, this is actually the rotation of the second element at node 2 that we're getting out of this system equation. Okay? So then we can back solve using those displacements to get the external forces or the constraint forces. This is normal. And then we can go and use this system of equations, right? We're going to basically take, for the element that we had the hinge, we can just multiply the stiffness matrix times the displacements that we got, and that will give us the forces and moments. You see, for the first element, that gives us a shear and a moment at the first end, and a shear and nothing, no moment, right? Because a 0 is a hinge. Now, we go back and we now look at the second the second stiffness matrix, we then take the stiffness matrix of the second element, which is normal, and we're going to multiply that by the displacements. But when we do that, you'll see we have 3 of these displacements already. We have the displacement at node 1. We have what we don't have is a rotation at node 1, because the rotation we got was for the other element. So we have the displacement at 2 and we have the rotation at 2. So what we can do is solve this equation. We have all forces though, right? We know the force in the first one was, you see the forces right here, right? We had the force in the first one, and we multiply this out, and this gives us our forces in that element. Then we can go and take that back solve for the one rotation. Once we have these 3 forces and moments, we can back solve for the rotation. That's by taking this system, solve that last part of the equation, and that gives us the rotation at node 2. So what that means is, so we're going to take the global displacements at both ends of element 1 to get the forces in element 1. We'll take the global displacements against the stiffness matrix of element 2 to get the forces in element 2, and then we use the forces in element 2 and back solve the last equation of that stiffness matrix to get the rotation at element 2. Does that make sense? Okay, and we see in this case, since this was symmetric, bar 1's node 2 has the opposite of the rotation of bar 2's node 2. Now let's take a look at what happens if we instead model our element on the first end on node 1 of the other element. Okay, we're going to use the same stiffness matrix, and now the first element is unchanged. There's our partial matrix and our full matrix, and now you'll see in element 2 we now modeled the hinge here. You see that? So it's the first node of element 2. This means we have this element is normal, and this element has the hinge at node 1. Note the typo here in my video slide. Okay, so we now are going to construct our global stiffness matrix and pose our boundary conditions in the same manner, and then we can go and solve our system of equations. Once again, we have a typo right here. Let's fix that. This is node 1 of element 2. Now you'll notice, since we applied the hinge, and let me draw a little more here, since in this case we've got 2 elements. This is a normal element. This is node 1. This is node 2. And this is the second element. And we actually have the hinge noted here on this end, which is node 2 of the second bar. See that? Okay, since it's in this one, you'll notice that this rotation that we get, or this displacement, is the displacement of both nodes. So you'll see this guy going like this. Since this is the one we modeled it in element 2, that means this applies to element 1, and you can see that it's a negative slope there, right? Now, to get the slope in this element going this way, this is the slope at node 1 of element 2. This here is the slope in element 1 at node 2, right? So this is the one we got since we modeled on this one. Now we're going to have to do another step to get the other one, okay? So we continue on, solve for our forces. We use our system equations. We plug in our displacements to calculate the forces in each, and then we back solve using these forces. We back solve to calculate using in the other element. So in this case, we put it at the node 1. That means we're going to go back to the stiffness matrix for element 1, and we're going to back solve this equation. That gives us the other result. So that's how we handle node hinges in bar elements or beam elements, okay? Basically, we're going to change the local stiffness matrix. We're going to go through the process like normal. We're going to be careful when we pull the rotation. We're going to take care of the rotation that we're going to get out of solving our system of equations is going to be the rotation of the element that has the hinge, but that wasn't modeled, didn't have the hinge modeled in that element. And then we will have to, after calculating the force in the element, back solve to calculate the angle of rotation of the same node in the other element, if we need to do that. Okay? That's all we got. Enjoy.